All right, this is kind of one of the interesting lessons that you've never seen before. This is not part of Algebra 1. You never did it in geometry. Completely new material we're tackling here. Some of you guys will recognize that there's a triangle here. If you see that triangle and you recognize the name of it, it's Pascal's triangle. It's a famous number pattern that allows us to do things. And one of the things it allows us to do is it allows us to take a binomial and expand it. And this is kind of an exploratory activity to get us to the point where we understand the Pascal's triangle. And then we understand how to expand binomials. That's just two terms raised to a power. All right? And from there, we can use that to find specific terms. Like I might be able to find the fourth term, which is the third position on this row right here. So let's start real simple. All right. If you read through this, basically what they're saying is, hey, you start at the top of this triangle, and then you can go left and get there, and then right and get here, and left and get here. In this lesson, this book, it explores this in a way I've actually never had it explored before with myself. I was taught a different way, and I'll show you that. It's a much easier way. They're basically saying, hey, how many ways are there to this path? All right. So there's one way. I mean, that's our start. And if I go left, I'm here. If I go right, I'm not. So there's really only one, and so we write the number 1. There's only one way to this path from the top. I go right. There happens to be 2 ways to get to this box right here, the middle box on row 2. Notice that that's row 0 and this is row 2. All right, so I can go left, right. There's one way. All right, I could go left and then right, and then I could go right and then left. There's the other way. So a total of 2. Let's try this guy right here, right? I could go left, left, right. There's 1. I'll put it right there. I could go left, right, left. There's 2. And I could go right, left, left, and that would give me a total of 3. So, and again, there's only one way to each one of those on the left side. And likewise, over here, I could go right, right, left. There's 1. I could go right, left, right. There's 2. I could start off going left and then twice to the right. There's a total of 3. Well, what we notice is we notice this right here. And I'm going to show you this once. I'm going to let you fill out the rest of this without me, and you should be able to. All right, I'm actually going to refer back to a completed chart later on. So if you waited, which I prefer you don't, then you should be able to finish this row right here. So here we go. If you'll notice that for every node, every box on here, the value is well, look at this. There's 1, and this one is 1 plus 1. Look, this box right here is 1 plus 2. So what you're really doing is you're taking the sum of the values in the 2 nodes above it, which makes sense, right? If there's 3 ways to get to this one and there's 1 way to get to that one, well, I could use these 3 or that one and get to this box of 4. It's really just 1 plus 3. And this side will always be 1, right? And this is 3 plus 3, which is 6. This is 3 plus 1, which is 4. And this is just 1 again. Notice there's a pattern, right? The ends are the same, and as we go in, we can see that there's matching numbers. There's some symmetry to this. I'm going to go ahead and do this next one. That's like 1 and 4. There's 6 and 4 is 10. And look, we get 6 and 4 again, which is 10 and 1 and 5. I would prefer, I'm going to pull this away. I'm not going to highlight it or anything because we're going to use this again. But you do it without me. I'm going to wait a little bit and I'll put it back up there. I'm writing really slow so you can beat me. I'm going to put it back up and check to see that you have the same thing. There's a lot of good ways to check, right? We can do the sums again, and we can see, hey, do the patterns match, and that middle 20 is 10 plus 10. All right. If you look at this bottom one, right, we've already done this. It says finish the last 2 rows, which we did. We could do another row if needed to. I don't think we need to at this point. So we're just going to say finished. And we've done the first page. So I'm going to hit you with the second page as well. So I'm going to pull this aside, and let's go to the second page. All right. So it says this. It says, I can relate Pascal's triangle to binomials. So what we're going to do is we're going to relate this Pascal's triangle, which we're going to see, right? And we're going to explore how this right here is related to, well, the binomial pattern that we noticed down here. I want to point something out, though. Let's write this. When we're doing combinations, right, we've got N and R, all right? And notice that both of them start at 0, right? Both of them start at 0. And as I come down here, right, N has to do with my row, which feels a little counterintuitive because we have an R over there. And R has to do with the position. So this would be the first position, first row. But realize that there is a 0 position right here. And there's a 0 position for every one of these. And then there's a 0 row. So as much as we want this to be the second row, it's really the first row, the second row, the third row, and the 0 row. And this is going to come into play later on. In fact, right now it probably feels super weird in your brain. So we're going to step away from this and come back to this soon. And let's go right here. All right. And let's expand these, right? Anything to the 0 power is 1. So a plus b, and that's just giving us a kind of a generic binomial, to the 0 power is 1. Well, in order to get it to the first power, I can take the 0 power and multiply it by the next power, right? Well, a plus 1 to the first power is obviously just a plus b, right? I said a plus 1, sorry. Well, in order to change it to this power, I take this term, so I'm going to write it out here. I'm going to take a plus b. I'm going to multiply it by the next term, a plus b. I'm going to FOIL this whole thing out, and I'm going to start giving them to you pretty soon. We know this. That's a perfect square trinomial. First times first is a squared. And I'm going to show the whole step here, ab, right? And then we do this, and ab, right? ba is just ab2. And then we go b times b, and we get this b squared. And we can see that these are like terms in the middle. So if I expand this, it's a squared, and we combine those like terms, 2ab, instead of just there's 1ab and 1ab. And then we get b squared. Well, if I took this and multiplied it by a plus b, right? If I multiplied everything on there by a, I'd obviously get a cubed. And if you need to see this, we can do this. But I'm going to show you the final answer. This is really just multiplying this entire thing, which is a plus b squared, by another a plus b. And we'd FOIL it all together and combine like terms. It's going to be 3a squared b plus 3ab squared plus b cubed. And then if we multiply that one more time, because it's to the 4th power, we would get this. We would get a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. All right, so we're going to notice some patterns. I'm going to pause it after this. Let me make sure I'm really going to pause it after this. I think I am going to pause it after this, right? And we're going to kind of start applying this knowledge. And we'll do 2 videos. The second one will be a little bit longer. What am I noticing about exponents on a? Well, it looks like the exponent that gives me this starts off with a. It starts off as the first exponent. So when this whole thing's raised to the 4th, a starts off as the 4th. And then it goes down 3, 2. I could write a 1 there. And since a disappears, it must be a to the 0. So I'm going to say this. I'm going to say a decreases by 1 every move. We'll say right. And likewise, there's no b here. And now we've got b to the 1st, 2nd, 3rd, 4th. b increases by 1. I'm going to go into ditto mode, every move right. All right? And look at the sums. The sums, look, if I take the sum of those exponents, well, that's 4 and 0, so that's 4. 3 plus 1 is 4. 2 plus 2 is 4. 1 plus 3 is 4. Oh my goodness. The sum is always n. And let's point out where n is on here, right? the sum of the exponents is always equal to the power that's on the binomial. All right, so that's something we're going to use pretty soon. All right, I know this is a lot, but we will get this. We got a long day in class to practice and get through this. All right, what do I notice about the coefficients? Well, this is awesome, and this is one of the main reasons Pascal's triangle works. And maybe you've seen it already, but I'm poking in here. Here we go. So look, this right here says I'm going to do the third power. I'm going to do the third power right here. Well, I come down to the row 3. Remember, that's really the 4th row in there, but it's since the first one starts at row 0, this has to do with my third power. 1, 3, 3, 1. Well, lo and behold, 1. Let's put that 1 in there, right? 3, 3, 1. Oh my goodness! Look, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. We could go up to this guy, right? We could say 1, 2, 1. 1, 2, 1. One above it. Ready? 1, 1. The coefficient's the number in front. 1, 1. The top one is just 1 with no A's or B's, right? Because we start off with a 0 power. So what we're noticing is, and let's just write simply what they do. They match Pascal's triangle. That is just awesome. They do. They match Pascal's triangle perfectly. So I'm going to pause this for right now. I'm going to say first 2 pages, and I'll talk to you guys tomorrow.